So let's review where we are on atomic structure. When I say review, it depends on what class you're in. If you're in Chemistry 1301, we're just reviewing what we talked about in detail in class. If you're in 1331 or 1332, this should truly be a review for you. So anyway, as we look at some of the rough history of how we've come up with our current idea of atomic structure, it started with Dalton's atomic theory. Dalton said all matter was made up of atoms. Atoms are indivisible. There are different types of atoms, but if an atom is one particular type, every other atom of that same type is identical to that atom. And so, for example, if we think about a hydrogen atom and an oxygen atom, hydrogen atom we'll just think about as being a little green ball, oxygen atom as being a bigger red ball. So every hydrogen atom, according to Dalton, would be a little green ball, every oxygen atom would be a little red ball. Then in the late part of the 19th century, due to experiments with the cathode ray tube, the plum pudding model, which I like to think of as the chocolate chip cookie model or blueberry muffin model, J.J. Thomson, the chap given credit mostly for this, and in this he says, well, as actually atoms are divisible. You can think of them as having a central nucleus which is positively charged and makes up both the mass and the volume of the atom, and then stuck to this nucleus, which is like the cookie or the muffin part, are the electrons, which would be like the chocolate chips or the blueberries. So a hydrogen atom therefore is now no longer just a solid green ball, but it's this green nucleus with an electron stuck to it. And then an oxygen atom we'll think of as being again bigger. We're still calling it red, but instead of it being indivisible, it has some electrons stuck to it. I've thrown in 8 for reasons that most of you should know. And again, the nucleus is the whole thing, it's the whole cookie part. Anyway, then right at the start of the 20th century, Ernest Rutherford carried out an experiment that led him to postulate the nuclear model of the atom. In this, electrons circle the nucleus in the cloud. The nucleus is still the big mass of the atom, but the electron cloud is what defines the size of the atom. And so here's our hydrogen atom, there's the nucleus right in the middle of it, okay, and then the electron is somewhere in this area here, and then again the oxygen atom, there's the nucleus of the oxygen atom, and it's got the electrons going around in the cloud outside it. So the mass is the nucleus, the size of the atom is defined by the electron cloud. Now, of course, we've gone even further than that, and we believe in the presence of subatomic particles which go to make up both the nucleus and the electron cloud. The nucleus, we say, is made up of protons and neutrons. Right? Protons have a mass of 1, a charge of +1. Neutrons have a mass of 1 and a charge of 0. And remember, with this mass, we're not saying it's 1 whatever, we're just really talking about it being in terms of relative mass. The fact that protons and neutrons have the same value 1 there, just means that they have the same mass. The charge part, well, protons being positive means that we believe protons repel each other if they come close to each other. Neutrons with 0 charge just don't care. They can be close to each other, they can be close to other protons, and so on. Now, having defined the nucleus as being made up of these subatomic particles, protons and neutrons, we talk about the electron cloud being made up of electrons. Electrons are teeny. We say their mass is 0. That doesn't mean they have no mass. It just means that relative to protons and neutrons, their mass is negligible. And of course, electrons have a charge of -1. This simply means, first of all, that electrons will repel each other because they have the same charge. They will be attracted to protons. Electrons are negative, protons are positive. And the fact that electrons are -1 and protons are +1 simply says that an electron is as negative as a proton is positive. So if we take this idea and we break it down for a given atom, first thing we can do is we can say, well, if you've got protons are plus and electrons are negative, protons are as positive as electrons are negative, that means that the number of protons is going to equal the number of electrons in an atom. Now, that number of protons is defined as being the atomic number. We give that the symbol Z. That is a very important number. That defines the type of atom. So for example, hydrogen is a type of atom. Every single hydrogen atom in the universe has the same number of protons in there. Not the same number of neutrons, but the same number of protons. Now remember how we said that the mass of an atom is the mass of the nucleus. We call that mass of an atom the mass number sometimes, and that's going to simply equal the number of protons plus the number of neutrons. Those are the two subatomic particles that have mass, as they each have a mass of 1. If you have 3 protons, well, that's a mass of 3. If you have 4 neutrons, that's a mass of 4. So if you have 3 protons, 4 neutrons, 3 plus 4, the whole atom would weigh 7. The mass number would be 7. The way we denote this with symbols is the mass number is A, the number of protons is the atomic number Z, the number of neutrons we use N, so therefore we have A, the mass number, is Z, the number of neutrons, Z, the number of protons, plus N, the number of neutrons. I mentioned a little second ago that a given type of atom, all the atoms have the same number of protons, but they can have different numbers of neutrons. This situation are called isotopes. Isotopes are very, very simply the same type of atom, so they've got the same Z, that means the same number of protons, same atomic number, but they have different number of neutrons. And of course, if they've got the same Z but different N, they're going to have different masses from each other. And that's how we refer to different isotopes, not usually by the different number of neutrons, but by the different mass numbers that they have. Let's look at an example. Chlorine. Chlorine has got a Z of 17. That means that in every single chlorine atom in the universe, as far as our theory is concerned, there are 17 protons in the nucleus. There are 2 isotopes of chlorine. 2 different kinds of chlorine atoms. One of those isotopes has 18 neutrons, one of those isotopes has 20 neutrons. So if we consider these separately, the one with 18 neutrons, using our symbols, N is 18. So the mass number of that isotope, 17 for the number of protons, 18 for the number of neutrons, 17 plus 18 is 35. We refer to that as chlorine 35, or we write it with a little superscript to the left there, 35 chlorine. The other isotope has 20 neutrons, N is 20, mass number therefore 17 plus 20 is 37. See, different mass numbers because different numbers of neutrons. Again, we refer to that as chlorine 37 or 37Cl with the 37 as a little superscript. One thing that confuses students quite a bit, so I'm going to throw it at you now and then we will do some examples in class, is what's known as the relative mass or the atomic mass. If we take a particular sample of an element, right, all of the isotopes are present in there. So we can't just say the mass of any atom in there is the same. We can if there's only the one isotope, but just about everything has more than one isotope. So therefore we need to talk about the average mass of the atoms in there. Now the average is always of course defined as being the total over the number. So in this case, if we've got a certain mass of an element, the average mass of each atom in there is going to be the total mass divided by the number of atoms. It's not just going to be the simple average of isotopes. The example I use in class here is your average on quizzes. In a quiz you could get maybe 2 out of 10 or you could get 10 out of 10. Well, the average score of a quiz is not going to be the average of 2 and 10 or 6. The average score is going to depend on how many people get 10 and how many people get 2. So the way that we can express that is the so-called weighted average. For the weighted average of anything, you simply take the values, so in this case it would be the mass of the isotope, or in class it would be what the different grades possible, so a 2 or a 10, multiplied by the fraction of the atoms that are that isotope, or in other words, if we're back to the class, the fraction of the students that have that particular score. So for example, in chlorine, we already know chlorine has 2 isotopes, chlorine 35 and chlorine 37. I'm telling you, and pretty much I'd have to tell you, you can't just look at the periodic table or anything to get this information, that in chlorine, 3/4 of the chlorine atoms are chlorine 35 And so the remaining fourth, and remember that if there's only two isotopes, you got to add these fractions together to get one. So if 3/4 are chlorine 35, there's a fourth remaining that are going to be chlorine 37. So therefore the average mass of chlorine in a chlorine sample is where we take for each isotope. So we got, here's an expression for 35, here's an expression for 37. For each isotope we take the mass times the fraction. So 35 is the mass, the fraction is 0.75. The other isotope, 37, is the mass, 0.25 is the fraction. Multiply for each one the mass times the fraction and then add those up and you get 35.5. We'll do a couple more examples, probably more complicated, when we do this in class.